Chris and Wouter.
Hey everyone, can you hear me fine? Yes? Great. Well, thank you for attending. My name is Chris. I'm the head of the GNC team at GAMA, so Guidance, Navigation, and Control. But we're a startup, so we're building a lot of things into a small team, including developing the onboard software. So just to give you a little bit of context about GAMA, so GAMA is quite a young startup actually. We are 2.5 years old, 20 employees, like 18 engineers. So we're really focusing on trying to build something that works. And so we are building solar sails. Does anyone know about solar sailing? Right. So for the one who are not aware of what solar sailing is, so we are building very huge mirrors in space. So starting from 100 meters squared and ramping up from there. And those mirrors use the power of the sun rays, the photons of the sun, to give momentum to the satellites. So it's a propulsion device. So we want to use that for exploration and for commercial also exploitation. But right now we are building just demonstrators, flight demonstrators. The two main missions are, the first missions are the demonstrators missions. The first one is Gamma Alpha. So we have launched it already. It's in space right now. We've launched in January on board the Falcon 9 SpaceX Falcon 9 rocket. And so we are planning the solar sail operations, deployment operations for this summer. The second mission is called Gamma Beta. And for the second mission, we are planning on measuring exactly the performance of the solar sail, whereas the first one was only focused on proving that we are able to deploy a solar sail because we're using very different technologies from the standard like structural booms that are usually used to deploy solar sails. But anyway, we just want to get to the cybersecurity part. And so the cool thing at Gamma is that we are using Rust for the flight systems and for the ground systems. So first of all, why and what's wrong with the normal approaches?
Yeah, so traditionally in aerospace, languages like C, C++, Fortran, ADA, and Simulink are used to implement the flight software. So that's traditionally, but aerospace also greatly values correctness and robustness of their implementations. And these languages are, some of them are quite old, and they not necessarily help in achieving that objective of correctness and robustness. Of course, nowadays we have more modern languages, but they're not used a lot in aerospace yet. So just to give a brief highlight, C, of course, is quite a basic language. You have not a lot of capability to express your intent as a programmer. And also you have these issues you have to deal with, like lots of things you can write down are actually not allowed by the language standard, but you're still able to write it down and compile it. The compiler will just generate code, but you've actually built something that exhibits undefined behavior. So ideally, we would like to have a language that does not allow this undefined behavior. And for example, Simulink, it's used a lot, especially by mathematicians and physicists. But that entire ecosystem is quite driven by the vendor of that language. So yeah, it's hard to develop if you're bound by only what the vendor applies. You do not have like a vivid community that creates tooling for you. So next slide, please. So at Gamma, we are using the Rust programming language just because we are curious. Who of you, raise your hand, is actually a software engineer or at least writes code? So
quite a lot, actually.
Quite a lot, yeah. Who of you have heard of the Rust language before? Who of you would like to use the Rust language? Who of you have actually used the Rust language?
3, 4,
okay.
5. Whoa.
Okay, that's more than we expected. I think.
Absolutely, for sure.
So just for the rest, to give a brief overview, Rust was made by someone, Graydon Hoare, who's a developer at Mozilla, as like a hobby project. At some point, it got adopted by Mozilla, and they even have it running now in their Firefox internet browser. The first stable release was in 2015. Nowadays, it's mainly a community-driven open source project with way more users than just Mozilla. So, for example, Amazon and Microsoft and other companies are also using it. And the main objective of the language is, at least, depends on how you look at it, of course, but it reduces memory management bugs, so it has memory safety high in the list of priorities.
One thing I'd just like to add is that usually when people think about Rust, they say, oh, it's a really modern language. Well, okay, so space is very slow for the adoption of new technologies, and that's normal. We're striving for reliability. But Rust is not such a new language, actually. The first completely usable and final version dates from 8 years ago already, and the development has started since like 15 years or 20 years. So it's actually really mature right now, a lot more than people think.
Yeah, next slide. So Stack Overflow does a annual, how do you say this, query, poll?
A poll, yeah.
Yeah, survey amongst all their users, what do you use at work and where are you from, that kind of question. But also, which language do you love the most, which is defined as do you use and actually like using instead of just want to use. But it's also the most wanted. Rust is also the most wanted language for a few years now. Yeah. And it's also quite popular, but that just means that has not necessarily a high adoption within companies. But it is indication that most programmers want to use it. This in contrast to languages we typically use in aerospace, like C and C++. I think C++ is like 24th most loved language. C 32nd.
They're very low in the list.
And Simulink is the worst.
No way, it's the last
one. It's in the bottom, yeah.
No way.
Yeah. So apparently programmers don't like to use the languages that aerospace likes to use. So that's maybe interesting for recruitment. So there are quite a few people that know Rust, so that's great. So I can maybe go a bit more in depth. If you're not a programmer, just politely listen. So what makes Rust suitable for aerospace and critically for safety, robustness, and correctness applications? So it has this really robust memory safety feature with the notion of strict ownership and lifetimes. So that means that there's always one or more owners of a language, but if you have more owners, then that implies that the memory spot you are using is actually read-only. So if you have a mutable piece of memory, that means that only one part of your code is able to access it. All your memory is also guaranteed to be initialized, so you cannot use uninitialized memory, and it's also guaranteed to be cleaned up. Furthermore, you can pass references. In Rust, we call those borrows. And you cannot do, for example, you cannot return a borrow from a function, as you can accidentally do in C++, which is undefined behavior. So it has these notions of memory safety and also thread safety, which I'll not go into depth about, which are very desirable for embedded or specifically aerospace applications. Furthermore, in embedded, we really like to integrate with foreign code. So, for example, a closed source binary or C code. And Rust has this notion of unsafe Rust. So it provides all these safe guardrails, but sometimes you need to drop them to integrate with foreign code because that foreign code does not provide the same guarantees. So you use the unsafe keyword, and the block of code that is covered by that keyword can do everything that C can, which is exactly what you want if you want to audit your code, because that means that instead of having to audit 100% of your code, you only need to audit like maybe 1% or less of your code for these kinds of issues.
One very important thing to add is that you may know about that concepts in C and C++ of undefined behavior. Well, in safe Rust, this concept just does not exist. You cannot have undefined behavior in safe Rust, which allows, so it exists in unsafe Rust. It's needed at some point in the language. But then if you need to test and thoroughly validate some code, then you can only concentrate on that part of the code, which in terms of velocity is a huge gain.
So as far as we know, we are the first operator of actually having Rust running in space. We know a few initiatives at the French Space Agency, at ESA, at NASA, and also at SpaceX that to at least try out Rust and evaluate it, or even use it in some ground support equipment. But so there is movement, but as far as we know, we are the first, so it's a point of pride, I think.
Exactly, for sure.
So it has been interesting for GAMA to use Rust as a startup because you have no prior code base, so it's relatively easy to get started. And I think also programmers love to use it, so it's nice to get programmers that are interested in it.
We can just say a word, 2 minutes, about the Ferrosine initiative, which is an initiative from the Ferrosystems company. And Ferrosine is a fully standards compliant, validated Rust compiler toolchain. So it's especially for mission criticals and safety critical systems. So they are trying to bring Rust into those kind of environments where you need to answer to ISO standards, DO standards like DO 178C, which you may know. So it's like there are a lot of initiatives trying to bring Rust into all of the industry which needs those kinds of features, like especially the safety features. And of course, this allows us to be really quick in the development.
Yeah, so it's nice to note that Ferrosine is supported by Ferrosystems, which is a Rust company, but also Ada Core, which is the company behind the language Ada. So it has some serious interest. Automotive is also very interested in using it. So the language specification exists, but the compiler is still a work in progress. So if you want to use Ferrosystem today, Ferrosine today, then you can help, maybe.
It's coming, yeah.
Yeah. Okay, so how many of you actually work as an embedded software engineer? Just as I'm curious. Okay, that's not a lot. So I'll really briefly mention one interesting thing of using Rust in an embedded context. So normally you have your microcontroller that's provided by a vendor. So in Rust we have these libraries we call crates. It's just a software library, but it has the name crate. So we have this specific notion of how you should implement an embedded project. And this helps really if you want to, for example, download an open source driver to access some peripheral. In C, this is quite of a hassle to just download code and get it running. In Rust, this already is the case. So you can just download an implementation and run it on a microcontroller that has never been tested before, and it just works. So that's really interesting. So I'll really quickly explain how they do this. So we have the microcontroller. It has a CPU, which is made, in our case, by ARM. So you have a crate that implements the ARM Cortex-M specific intrinsics, like atomics. You have your peripherals, and they need to be accessed by registers. So the vendor provides an XML file, an SVD file it's called. And we generate a crate to access these registers automatically. So this is not manual process, this is an automatic thing that's generated for your specific microcontroller. Then we have this notion of a hardware abstraction layer. Most other systems also have this, but this is standardized in Rust. So for example, SPI, which is a communication bus interface, the notion for that, like a Java interface, has been standardized. And so drivers are just implemented on that interface. We call it a trait in Rust. So if you have this from your vendor, your SPI interface definition, and you have your driver that has been implemented by someone else, those two can be coupled automatically. Then you have a board support crate. So which kind of devices do you have on your PCB? We do not use this at GAMA because we directly implement the application.
This is a completely optional layer.
Yeah, exactly. And you can also run a real-time operating system. Let's explain it right now.
Yeah. Just before I talk about the real-time operating systems, one great thing with Rust and something that's very surprising when you're coming from a C or C++ background is that you just need like one command to cross-compile for your architecture. It's just very, very seamless and impressive how easy it is to just try out new things, like create new projects, just cross-compile them, it just works. So that's great. But for the real-time operating system, so this is the state of the ecosystem right now. As you can see, compiles unstable. Well, there are a bit of red crosses. Basically, so in GAMA, for our flight software, we're using FreeRTOS, which is implemented in C. So it is the only part of the flight software that is implemented in C. For this exact reason, is because the current real-time operating system environment is a bit lacking. So many are trying to get compiling like a native Rust compiling unstable with a real full operating system, including thread, like normal threading preemptive capabilities, but that's not the case yet. So that's the only part where we're still dependent on C right now in our architecture. So it's been very well tested. We're very confident in that, but in the future we may want to also develop some parts of real-time operating systems. So now how we use Rust in practice in the company. So we are a startup, we like having fun names. So for the flight software, it's called Shrek, and the ground control system is called Fiona. They communicate together through CSP, CubeSat Space Protocol. So those are both implemented completely in Rust, and then we have test benches and mission simulators, which also are completely implemented in Rust. On the ground side, the dynamics framework is implemented in Simulink, because that's what physicists use, of course, and we are a lot more efficient with Simulink for physics. For the rest, it's Rust. Let's dive just a tiny bit into the flight software. So libcsp and FreeRTOS are dependent together and are the parts of the code that are in C. All the rest, for example, the failure detection, isolation and recovery code, telemetry, telecommand management, all of the GNC logic that we needed to implement ourselves because the solar sails needs very specific GNC code. Then we implemented all of that in Rust successfully and basically had almost no problem with it. Yes, we're very happy with how it works. And so I built a little diagram of the architecture. It's not really important. So yes, we have multiple tasks within FreeRTOS. Every task is written in Rust, and they interact with external devices. And they interact together through some message and response queues, which is a protocol that we have developed for ourselves. In terms of the test benches, so we have a ground-based test bench. So it's a hybrid test bench. It includes real hardware, like copies of the flight hardware, and simulation of some parts, the rest of the flight hardware. So basically, we're testing our code running on the real hardware, and the rest of the some parts of the platform are just simulated. And so all of this mission simulation code is written in Rust also. Finally, for the mission control software, so it's quite a simple architecture, including a data manager and a web server. All of that is also written in Rust. For the web server, it's very, very, very efficient. It uses asynchronous programming. It's really out of the box, a very simple solution. And to be honest, we didn't need much effort to make it completely run with all our code. So it's really practical. We really like that. Let's discuss a bit about product assurance, because that's one of the main things. We want reliability for the space systems. So unit testing, of course, especially. So all of that we will be especially focusing, of course, on the unsafe parts of the code. So unit testing, fuzzing. In Rust, we also have property-based testing and model checkers. For example, there is what's called the CANI model checker, which helps a lot in automating the proofs of that the implementations are correct. And of course, we would as a startup, we like to go really quick and go to in-flight testing. But hardware in the loop simulations and integrations testing, we're doing them also. So yes, we are implementing kind of the whole range of product assurance approaches. Of course, we're trying to cut as many corners as we can, because that's for the velocity. But Rust allows us to keep a very, very strong baseline in terms of, especially in terms of cybersecurity, where we don't have null pointer dereference, we don't have Stack Overflows. That, I mean, that's just something that doesn't exist within Rust safe code. So, are we happy? Yes, we're very happy with the Rust implementation. We will keep using Rust for like the foreseeable future in the company. There are some downsides, of course. Mostly, it's very hard to find excellent developers. Since this is a new programming language, then all the embedded developers are usually use C or C++. So when we're interviewing, oh, have you ever heard of Rust? Then yes, sometimes, a little bit. Have you ever tried it? Not always. So finding very excellent developers is difficult, but it's getting easier. I've been noticing that in the last few years. A lot more people are getting aware of memory-safe languages and adopting them. And one downside I've spoken of is the real-time operating systems. Some parts of the ecosystems, especially for like mission-critical systems, are still lacking. But our company and other companies like Ferrosine Systems and like Tweede Golf are pushing towards making this ecosystem really complete and usable out of the box. That's it for our discussion. Feel free to ask any question. Thank you very much for your time and attention. Right on time.
Yeah, so we'll take some questions. Any in the room right here before I jump online?
Thank you for the presentation. I'm not fully familiar with Rust, but is there a garbage collector? And if yes, is it an issue?
No, so there's no garbage collector unless you want to. So you can, of course, use an optional garbage collector. But it's like it's more like C++ in the sense that you automatically what goes out of scope is just destroyed immediately. So
the guarantees of Rust are held by static analysis. Like it's not runtime. There is no runtime for Rust.
Yeah, so you kind of alluded to this. I want to throw this question up just to say, besides the, I guess, getting expertise, their question is, Rust seems too good to be true. Is there a catch, i.e. disadvantage? Outside of the staffing perspective, is there a technical disadvantage that you've seen?
So I think the major disadvantage that you hear from like surveys is Rust because you tend to need, if you have a piece of memory and you're using it, you tend to keep it around a bit longer. So if you want to be like really efficient in your memory usage, you might need to be more considerate on when you try to deallocate something. So explicitly dropping it, that's one thing that might be, but it's more in the control of the programmer. Furthermore, maybe compile times.
Compile times are quite a bit longer than C and C++ usually, though there are a lot of things we can do to help reduce that. In terms of performance, I think it's a good question that a lot of people have. How does the performance compare? We're usually under 5% difference with C. Of course, it's very dependent on the application, but the performance is like very, very satisfying.
Awesome, thank you. We'll go to one more in the crowd, but answer this one while I walk over. So, public crates are regularly updated, which means you can read it, but it becomes difficult to guarantee immutability is what they're saying. So how do you account for that immutability correction or in the flight software?
So Cargo has a capability called vendoring. So that means that you, besides locking your dependencies and the specific versions of your dependencies, you actually get a hard copy of all the dependencies. And we put this in the source tree. So if we want to update the dependencies, that's an explicit process. And then also these Git repos tend to get a bit big, but you get all your source code, and even if there's no internet anymore, you can even compile it.
Yeah, and this allows also for, because the updates are explicit, this allows for code reviewing at the moment of updating, so of course, depending on how much crates you use can be a bit tedious, but this allows for a very good code review process and static analysis process before you integrate those new versions of the crates within your application. Still, the cargo and the dependency management can be an issue in terms of security because of supply chain attacks. I mean, because it's easy to distribute some code, then it's easy to get some bad code in there. But this vendoring system helps a lot, and if we are careful with it, and if we do our due diligence, then it's completely fine, no problem.
Yeah, so there's already a decent size community of like flight software and libraries written in C and C++. How well do these libraries integrate with your Rust system, and how well do you anticipate that your systems might integrate with a C++-based flight software?
So right now, the only libraries we're using, for example, in C are libcsp, so the CubeSat Space Protocol. Integration is very seamless. We need to use a little bit of unsafe code to have a wrapper around that and to provide safe access to those crates, to those libraries. Usually, it's absolutely no problem interfacing with C and C++ code. Writing a wrapper is something very simple. There's usually no technicalities in writing a wrapper around a C or C++ dependency, so no issues with that.
Okay, thank you.
Any other questions in the room? All right, there's a couple more online here. So I like this one. So are there benchmarks, experiments to demonstrate the superiority of Rust with respect to other languages against cyber attacks? So this would, I know there's a lot of historical evidence on the C, C++. I've seen several publications, White Source being one of them, that published the propensity of vulnerabilities and cyber attacks per language with C, C++, and Java and others. But do you see one with Rust? Has there been one published?
So what I have seen in the past few years is that major companies like Microsoft and Amazon are adopting Rust mainly for the memory safety feature. So they have done internal studies, and I think they also published a blog post about it, that
Yes.
that they notice a significant reduction in, or maybe even complete elimination of these kinds of issues when they've ported part of their code base to Rust.
Yeah, so I don't have the link offhand, so whoever asked this question online, if you Google White Source, and they're a vendor for like source code analysis for CVEs, they have a study they did for like 20 years of all the vulnerabilities that have been exploited in the wild, broken down by language. So I don't know if Rust was in that study because it stopped in 2018, which is kind of right when Rust was picking up steam. But it'll be interesting to see what type of that looks like in the future. But well, give you guys a hand. Good job. Thank you very much, because very interesting topic.